All right, guys, we have 12.2 techniques for evaluating limits. We're going to review some of the things that we talked about in 12.1 about, basic limit concepts. We're also going to look at some more advanced techniques for finding limits strictly algebraically. All right, so go ahead and pause the video when these come up if you want to go ahead and try these, because I'm going to just go ahead and go straight into them. Okay, so the first one we have direct substitution. That's going to be a common thing that we'll want to try right away with limits. Just see if we can do direct substitution. So we just take whatever our number that we're approaching is and kind of plug that directly into the function. So in that case, we're just going to plug -4 in for all of our x's, evaluate this, and kind of make sure everything looks right. A lot of 4's here. All right, so -4 squared is 16. 4 times -4 is -16 plus 4. That's 0 plus 4. So this limit is going to have a value of 4. Now, even when you can plug one in directly, you got to be a little bit careful. You got to make sure you understand what type of function you're looking at and what type of graph that would create, and make sure there's not any jumps or gaps or weird things that may be actually happening at this value. Obviously, we know that it's not undefined, so that's good, but there could be something weird happening that you need to be aware of. In this case, this is just a regular parabola, not anything weird going on there, so this is going to be our limit. All right, now the next two, we're going to graph these and kind of evaluate their limits. We're looking at both as x approaches 0. So I'm going to go ahead and go to Desmos and take a look at what these do. So we have, first one was absolute value of 3x over x. Okay. Don't really know what's going on there. There we go. So in this one, we can see that as x approaches 0, so 0 is right here, on the left side, we're approaching -3, and on the right side, we're approaching 3. So since those limits on each side are different, we say that this limit does not exist. So the limit of our function f of x as x approaches 0, in this case, does not exist. This is one of those three cases that we know where a limit does not exist, where the right-hand limit and the left-hand limit are approaching different values. We could write that out this way. We could say the limit as x approaches 0 from the left side, from the negative side, is -3, and the limit of our function as x approaches 0 from the positive side is 3. Since these don't agree, we say the limit does not exist. All right, now our other function was sine x. I should put the fraction first. Sine x over x. All right, and again, we're looking at this function as it approaches 0. So it's worthwhile. In this case, at 0, it kind of looks like it, okay, well, it is undefined, and that makes sense. 0 in the denominator here would make this a division by 0. It is undefined at 0. But as we kind of follow it, it's approaching whatever this number is on both sides, and that looks like 1. So if we were to, zoom in a little more, yeah, okay, it's definitely 1, and the more we know about sort of sine, as we're really close to it on both sides, we are getting really, really close to 1. So since, as we look at it's happening from both sides, so from the left and from the right, we're approaching the same value, we say that this limit would be 1. So the limit as x approaches 0 of this function f of x is 1. Even though it is undefined, we have a hole there. As we look on both sides, it is 1 right there. There are ways to algebraically evaluate this limit as well, but we would need to know a little bit more about trigonometry that we have not studied yet. All right, so let's go ahead and go back to our notes here. We're going to kind of try to remember some of the things that we've done up to this point. So far, we know how to evaluate a limit using direct substitution. We know how to evaluate a limit from a graph. We can look at that and kind of trace it. And also, we've created a lot of tables to estimate limits as well using Desmos. So We're going to keep using these techniques, but we're going to add a couple more skills to this. All right, so we already briefly mentioned here one-sided limits. You know, if we put a negative after the value that we're approaching, that means we're approaching from the left. And if we put a positive symbol, a plus symbol, that means we're approaching it from the right. For a limit to exist, the left side limit and the right side limit must agree. They must converge on a single number, not different numbers. So in this case, right, we had one approaching -3, one approaching 3. Therefore, we said the limit does not exist. There are other times where limits do not exist, and those happen usually around what's called a discontinuity. We have a couple types of discontinuity. We have a hole or a point. That's what we were looking at in the second one, where it was sine of x over x. There was a particular number at 0 that it was undefined, but it approached it on both sides, and it was just a single point where it was not undefined. We have vertical asymptotes. We didn't see any of those in our examples yet, but we've seen them a lot. Anytime we have a vertical asymptote, that means our graph is going to increase or decrease without bound as it approaches that asymptote. So it's either going to be going to positive infinity or negative infinity. Remember, that is another case where we say our limit does not exist. So if our function is approaching either infinity or negative infinity, the words that were used there was to increase without bound or decrease without bound. We say the limit does not exist. And jumps. That's actually like that example of the absolute value function we were looking at, whereas absolute value of 3x over x, we had a jump here or a gap. It approaches a different value on both sides, so again, doesn't exist. The third time where a limit does not exist is when it oscillates between two numbers kind of violently, uncontrollably. If you look at the function of sine of 1 over x, you'll see an example of that. As it approaches 0, it's just oscillating kind of infinitely quickly. The closer we get to 0, the more it's oscillating, and so it doesn't actually approach a set value. Even though you know, it may appear that it does or something, it still does not. All right. So here is an example of a function with actually two different types of discontinuity. We have a hole at -2, and we have a vertical asymptote at -3. And we're going to kind of examine what's going on with this function to see that. And what we need to understand is for rational functions, it's really all about the denominator and what can be factored out and what can't be factored out. Holes can be factored out. Vertical asymptotes cannot. So if we factor this, we need two numbers that multiply to 6 and add to 5. So that's 2 and 3. We get x plus 2 times x plus 3. And x plus 2 on top. So notice at -2, which this factor right here is causing a problem. If we plug a -2 in there, we're going to get 0. So this factor is causing us to get 0 in the denominator. It can be canceled out. We have an x plus 2 on the top and the bottom. Those can go away. Whereas this factor and -3, the other one that makes a 0, can't be factored out, can't be canceled out. Therefore, we'll remain with this vertical asymptote. So what does that let us do? So we just said that this denominator factors as, let's write that out again. It was x plus 2 on top, and then it was x plus 2 times x plus 3, right? Those canceled out, and we were left with a function that could be said to be algebraically equivalent, but not technically totally equivalent, because we're factoring out a discontinuity, so it'll be a little different, but algebraically it's the same. Now, by direct substitution, we were not able to evaluate this limit as x approaches -2 of this function. But we couldn't do direct substitution here, but we can in this new function, right? I can actually plug in a -2 here because it doesn't cause that problem anymore. Since we've canceled out the factor that was causing us to get a 0, we can now actually evaluate it. And so 1 over -2 plus 3, we get 1 over 1. So this limit is 1. And we could see that on the graph last time. but it's not always so obvious to see it on the graph. So it's useful sometimes for us to actually factor and simplify this out algebraically, because sometimes it might be approaching a fraction or something like that, and it's just not super obvious what that value happens to be. Let's clear that and let's actually go back just for a second. Yeah, so you can see that it is approaching 1 here on both the left and right side. All right. Sorry, we call this a removable discontinuity because we can actually factor out the factor that's causing the discontinuity. So we can remove it and then use direct substitution. All right, so really quickly, we can do these here. These are all going to have the same issue. They're all going to have a hole at whatever number we are looking at. Some of them are more obvious than others, but what we can do is we can factor all of these and remove this hole. So let's go ahead and do that. So this denominator here can be factored. So we saw the x plus 1 on top. Multiply to 9, add to -8. Pause it if you want to do that factoring on your own. We're going to get x minus 9 and x plus 1. So by removing the factor that causes a discontinuity at -1, we end up with this function, which is algebraically equivalent, but not exactly the same because we did remove a discontinuity. Now we can plug it in. We get 1 over, really shouldn't have an equal sign there. I should not do that. I'm evaluating this limit now because I can actually plug that number in. 1 over -1 minus 9, that's going to be 1 over -10 or -1/10. So the value of this limit is a fraction, which would have probably been a little bit more difficult to see on the graph. Let's keep moving forward. Let's take a look at this one. So on the top here, I can see that we do have a GCF between these. These both have an x and 5 as a common factor. So 5x times x minus 2 over x. And we're looking as x approaches 0. So obviously a 0 in the denominator is bad, but we can cancel that out there. We have an algebraically equivalent function that has taken out this discontinuity, though, of this. And we should just be able to plug in 0 there. So that's going to be 5 times 0 minus 2, 5 times -2, we get -10. So our limit here, as x approaches 0, is -10. All right, and the last one, let's do some red. So I'm noticing a GCF here of 3. So 3 times x minus 3. And here we have classic difference of squares. This is x squared minus 3 squared. So my denominator can factor as x plus 3 times x minus 3. And yeah, there we go. The minus 3 cancels out. That's what's causing our discontinuity at 3, because if we plug 3 in there, we get 0. So now we end up with our algebraically equivalent function with the discontinuity removed. We can now evaluate this at 3. So we get 3 over 3 plus 3, which is 3 over 6, which is actually a half. 1 over 2. So we were able to remove all of those discontinuities, so those were holes, and then evaluate it just using direct substitution. So it's a powerful strategy, something we're going to be doing a lot, and kind of we'd prefer to do this over looking at the graph. The graph is an estimate. Obviously, we can be extremely accurate on the graph too with our estimates, but confirming with algebra is really the way we want to be doing this. All right, let's go ahead and take a look at some other things we can do. Sometimes it's not so obvious. Sometimes we can remove a hole by doing what's called rationalizing. So rationalizing, well, usually means to remove radicals from either the numerator or denominator of a function. Usually we're talking about the denominator, but in this case, it can be wherever we want. In this case, we have this one right here, and it's pretty easy to see we do have a discontinuity. If we plug in 0, that's going to be an issue. There's no obvious way to factor this, but we do have a radical, so that's going to lead us to think maybe we can do rationalizing. So rationalizing makes use of our difference of squares factoring, the a squared minus b squared can always be written as a plus b times a minus b. Well, if you have one of these two, if you have an a minus b or an a plus b, if you multiply by the other one, you get this nice result here where you actually just sort of end up squaring both things, and there's no middle term like you would usually get when you multiply two binomials. These are called conjugates. Um, yeah, I'll use that language of the conjugate of something. Anyway, you end up basically squaring them. So that's useful because that's how you get rid of a radical, is to square it. Well, get rid of the square root by squaring. So this is my a minus b. So I need to multiply the top and the bottom of this function by the conjugate of a minus b, which would be a plus b, which in this case would be root x plus 1 plus 1. It's not going to be super obvious that this is going to be helpful right away, but we'll see eventually it is. Now, and again, this is my a plus b. So again, knowing how my difference of squares multiplication goes into this, essentially I'm just going to square this, which gets rid of the radical, becomes x plus 1, and square 1, so it'll be minus 1, right? That's my a squared minus b squared. On the denominator, I'm not actually going to multiply this all out because, again, my goal is to cancel out the thing that's causing the discontinuity, so I do want to cancel this x out. So there we go. That radical shouldn't extend over that plus, but I'm not going to fix it right this second. We know what it's supposed to look like. It's supposed to look like that. Hopefully we can see on the top how the plus 1 and the minus 1 here are going to nicely cancel so that we end up with x on top and an x on the bottom. Cancel those out, right? So our algebraically equivalent function would actually be this, 1 over square root x plus 1 minus 1. Now, we can plug in 0. It's not going to cause an issue. So to evaluate this limit now using direct substitution, I'm going to do 1 over square root 0 plus 1 plus 1. That should be a plus. I mistake there, right? That's a plus in this function, should be a plus there. Here we go. We have 0 plus 1 is 1. The square root of 1 is 1. So I end up with 1 over 1 plus 1, which is 1 over 2. So the value of this limit is 1 over 2, 1/2. So this process right here is called rationalizing. We're removing a radical from a particular location. Again, it's not obvious that it's going to be productive, but in these types of problems, it will be. Let's do another example, obviously, because that's what we do. All right, so again, rationalizing. We got some radicals here. And again, if I plug in a 3, root 3 minus root 3, we get 0 on the bottom. So I'm going to need to get rid of that by rationalizing. I'm going to use red. I liked the way that showed up. So this is my a minus b, right? A minus b. So I need to multiply by a plus b. So that's going to be root x plus root 3. That is my a plus b. And then what is my a squared minus b squared? So that's going to be root x squared is just x. Root 3 squared is just 3. So there we go. That's great. Got rid of those radicals. And now we need to multiply the top by this as well. But in the part that we're not rationalizing, I'm not actually going to multiply this out. And another thing, I'm going to go ahead and factor this, because this is factorable. And one of those factors is going to be x minus 3, because this is just difference of squares. This is x plus 3 times x minus 3. So I'm going to leave this all factored out. So it's x plus 3 times x minus 3 times that thing. And then the only thing that actually cancels out here is our x minus 3's, which is fine because that is causing an issue in our denominator still, but it's canceled out. So our algebraically equivalent function that we can now use direct substitution on is actually just x plus 3 times root x plus root 3. Now, we can use substitution on this one. We can plug in a 3. So I end up with 3 plus 3 times root 3 plus root 3. That's going to be 6 times 2 root 3, which is actually just going to be 12 square root 3. That is an exact value. That's another reason to be using rationalizing, is a lot of times when we're needing to use rationalizing to evaluate our limit's going to involve a radical. It is not going to be obvious that this is the exact value of our limit by looking at the graph, because this is an irrational number. We're going to be able to see that it's approaching something that actually is this number, but it's not. We're not going to be able to give an exact value of it just by analyzing the graph. We're going to see that it's approaching whatever the decimal version of this would happen to be. So 12 times square root 3. We would see on our graph that it's approaching 20.7846, whatever that ends up being. But again, the exact value would be impossible for us to know what it actually is without the algebra. All right, last thing we can do here with limits, or the last thing we're going to do here with limits, is evaluating difference quotients as h approaches 0. This is really important because this, in calculus, this is how we define the derivative, which is going to be the kind of first major calculus concept that you're going to be learning about when you get in there. The derivative of a function is a function that represents the rate of change at any particular x value. And so the derivative is a very powerful thing in calculus. And knowing how it's done is going to be super useful. So we're going to be looking as h approaches 0, which again, obviously, discontinuity. It can't do it. So we have to do some algebra with this to actually be able to remove that discontinuity, if we can. And that could take on any form that we may have learned up to this point. Could be just some simple algebra. It could be factoring things out and canceling them out. It could involve rationalizing. There's all kinds of things that may come up depending on the function that we're looking at. All right, so let's go ahead and look at some examples of doing this. So here we have a simple polynomial function, x squared minus 2x. Let's go ahead and figure out this whole difference quotient piece. So f of x plus h, right? Remember, that's plugging in x plus h for our x's. So we want to figure out what that is. So that's going to be, so squaring this, we get x squared plus 2xh plus h squared minus 2x minus 2h. So that's what f of x plus h is equal to. Obviously, this is our f of x. So let's start writing some things in there. 2xh plus h squared minus 2x minus 2h. Now we're subtracting f of x, so we're subtracting this whole thing. And all of this is over h. Now we got to be careful here. This is a place where people make a mistake. They forget to put parentheses around this function. We are subtracting the whole function f of x, so we do want to put that in parentheses. We need to make sure we're distributing that subtraction here. So we end up with minus x squared plus 2x. Now, let's put together what we can. Let's cancel out what we can. We have x squared and minus x squared. So those can go away. We have negative 2x and plus 2x. That's it. That's all we got. So let's rewrite that. 2xh plus h squared minus 2h all over h. This is great. This is the result we're looking for. All of these things on the top have an h in them, so I can actually divide the h through. When we do that, right, that's going to cancel. We're going to remove one of those, so we'll have h, and we'll remove that. divided it through to each term. Each term has to be divisible, otherwise we can't do this. So I had to divide all three. So that result is going to be 2x plus h minus 2. And we have gotten rid of that h in the denominator, which was causing our discontinuity as we approach 0. So as we approach 0, this becomes 0, and our derivative function would be 2x minus 2. There we go. Again, this one was a little bit easier. It was more straight algebra with this. They can be harder. They can involve factoring and rationalizing and such. All right, let's look at another one. Okay, so we have this function here. I'm going to kind of do the same thing I did before. I want to figure out what f of x plus h is. So f of x plus h. That's going to be 1 over 5 minus x plus h. Distribute that negative, we end up with 1 over 5 minus x minus h. Okay. So that's what it is. That's not ideal, but it is what it is. All right, so let's go ahead and substitute these things into here. So we have 1 over 5 minus x minus h minus 1 over 5 minus x. We could put parentheses around that. It's not strictly necessary here because as a fraction, we know we're subtracting the whole quantity over h. Now, obviously, this is our discontinuity. That's what's causing the major issues here. But also, these are just not super desirable. We want to be able to get rid of some things here. So we are dividing by h. That could be thought of as the same as multiplying by its reciprocal. So that's something that we can do. We also maybe want to put these two things together. A lot of algebra that can be done with this problem, and that will be done with this problem. So we got to figure out what in the world we can do here. So okay, so what we're going to do here is we are going to try to get rid of these less pleasant fractions. So we're going to multiply the top and the bottom of this by the lowest common denominator, which is actually just going to be both denominators. Not ideal, but that's what we're going to be doing. So we're going to be multiplying by 5 minus x minus h and times 5 minus x. Got to do that on the top and the bottom. Okay, so on the bottom, I'm going to go ahead and leave it factored for now. I don't suspect I'm looking to cancel this out, so I kind of want to just get rid of that later on. On the top, I am actually going to have to multiply this all out, so a little bit messy, but that's okay. So on the top, when I multiply this in here, the 5 minus x and 5 minus h is going to cancel out, so we just end up with 5 minus x minus, and then when I multiply it here, the 5 minus x's will cancel, and we'll end up with 5 minus x minus h all over. All these things multiplied together. So h times 5 minus x minus h over 5 and 5 minus x. Okay. A little bit of algebra here. We've got to distribute this. So we end up with minus 5 plus x plus h. And we can kind of see what cancels the positive 5 and the minus 5, the negative ax and positive x, and so just h on the top over h on the bottom, 5 minus x minus h over 5 minus x. H's cancel, we've got 1 on the top now, and now should be no problem to go ahead and directly substitute. Since we canceled out that h in the bottom that was causing our issues, and we plug that in, we put a 0 here where this h is. This ends up just being 5 minus x times 5 minus x, which is the same thing as 5 minus x to the second power, because we have the same thing multiplied by itself. So this would be our derivative of function there. That one was pretty tricky. Lots of fancy algebra that we had to pull out there. All right, last example here. We have a radical function. We're going to plug that in. I'm going to start the same way I did before. I'm going to not mess with things so much. Okay, figure out what f of x plus h is. So that's going to be root 2 times x plus h minus 1. So that's going to be radical 2x plus 2h minus 1. Okay, that's easy enough. So we get 2x plus 2h minus 1 minus 2x minus 1 over h. Here is our radicals. So this is where we're going to be doing some rationalizing. Really the only thing left to us at this point. There's no way to factor that. There's not even fractions we could put together. So right here we have a minus b. So I need to multiply by a plus b. So that would be 2x plus 2h minus 1 plus root 2x minus 1. So that's our a plus b. Got to do that on the top and the bottom. So I'll go ahead and write it out. Not gonna multiply that out on the bottom. I'm just gonna leave that written as it is. So it's gonna be h times 2x plus 2h minus 1 plus 2x minus 1. Okay. On the top, however, we do need to multiply these out. So a minus b times a plus b is going to end up being a squared minus b squared. So squaring will get rid of our radicals. So this squared minus this squared, so minus 2x minus 1. Since I'm squaring and I'm subtracting that whole quantity, I do want to put the parentheses there. When I distribute that negative in, we actually end up with negative 2x and plus 1. And that cancels out here, 2x and negative 2x, minus 1 and plus 1. So we end up with just 2h on top over h times radical 2x. Probably shouldn't have written that in. I'm gonna change my choice there. I think the yellow shows up all right, but I think black also does too. So 2h is what we have on the top, right? Yeah, nothing else. So 2h over h. That's where we're going to get those to cancel. And then I'll write out the rest of this. Root 2x plus 2h minus 1 plus root 2x minus 1. That extends there, and this should extend over the whole thing. Okay. Now, we have canceled out that h that was causing the issue. We still have one more h, so we can plug in 0 there. So that becomes 2 times 0, which is 0, and this just essentially goes away. Now we have 2x minus root 2x minus 1 plus root 2x minus 1. We have the same thing left on the inside of there. So we can say we have 2 of those. I'm going to erase some stuff here just to write this final result in the box. Kind of collect what we have. We have a 2 on top. Ooh. We have a 2 on top. What we have on the bottom here. So again, we had a root 2x minus 1 plus a root 2x minus 1. So we have 2 root 2x minus 1. Messed up. Those 2's are going to cancel. So let's go ahead and erase those 2's just to make it easier for our final answer. 1 over root 2x minus 1. Again, pretty challenging one. because we had those 2's that ended up canceling here, right? So that's where we end up getting that. Whew, another tough algebraic one.